Our greatest glory is not in never failing, but in rising every time we fall. So, hello my shimmering stars, I Shaurya Grover welcomes you to Victory Batch. Students, we have covered a lot of lectures in physical chemistry and today is our last lecture of physical chemistry in Victory Batch. So today we are going to cover ionic equilibrium, which ends our physical chemistry for class 11th. I hope so. You have understood all the chapters very well and you have gained a lot of knowledge also, right? So students, now we shall proceed towards our lecture. In ionic equilibrium, first of all, we need to understand that what do you mean by equilibrium? So let us look toward our first segment, that is, what do you mean by ionic equilibrium? First of all, if I move to the previous lecture, chemical equilibrium, what was equilibrium? It was that state at which certain measurable properties such as, pressure, volume, color, density, they do not change with time. That was equilibrium, right? So we shall write over here, equilibrium is that state at which certain measurable properties such as volume, pressure, density, color don't change with time. Don't change with time. So that state is equilibrium. Now the question arises that, ma'am, what do you mean by ionic equilibrium? If I talk about ionic equilibrium, it is the equilibrium which is established between unionized molecules and the ions of the solution of weak electrolyte. Okay. So if I define ionic equilibrium, it is the equilibrium established between unionized ions, okay, unionized ions and the ions of solution of weak electrolyte. Now what do you mean by this definition? See, if I divide ionic equilibrium into two halves, one is ionic, another one is equilibrium. Ionic refers to the dissociation into ions, right, the cations and the anions, and equilibrium is the state at which all the measurable properties do not change with time. Now what do you mean by ionic equilibrium? In other words, while talking in the terms of ions, how would I define it? It will be that state or it will be that equilibrium which is established between what? Between unionized, which is not ionized. Okay. For example, if I take case of CH3COOH, now it is not ionized, it is unionized, and the equilibrium that is attained between the ions of the weak electrolyte. Now when I am ionizing it, it is further ionized into CH3CO negative and H positive. These are the ions of the solution of the weak electrolyte, while this is the case for the unionized one. So when the equilibrium is attained in between these, it is referred to as ionic equilibrium. Now what do you mean by weak electrolyte over here? The question arises. Basically, weak electrolyte is that electrolyte which partially ionize into its ions. Strong electrolyte is the one which completely ionize. Okay, so that's why for the weak electrolyte we put a reversible sign, because it is partially ionized. It is not completely ionized. Clear? Now students, this was our first segment in which we got to know about what do you mean by ionic equilibrium. We shall proceed towards our next segment, that what do you mean by electrolyte. If I talk about electrolyte, as I have already told you in the given definition, that weak electrolyte is the one which is partially dissociated or partially ionized, right? So let us divide electrolyte in the terms of dissociation only into two categories. Number first is strong electrolyte. The very first is strong electrolyte. The second one is weak electrolyte. Okay, if I talk about what do you mean by strong and the weak electrolyte? Strong electrolyte is the one which is completely ionized. That means it is completely dissociated into its ions. Okay, so here I can say that degree of dissociation that we studied in the previous chapter also, degree of dissociation is 100%. Over here, degree of dissociation, that means the tendency to break into ions, okay, it is equivalent to 100% in the strong electrolytes. And when I talk about the weak electrolytes, if I would define weak electrolytes, these are the electrolytes which are partially ionized, or we can say which are not completely ionized, which are not completely ionized in other terms, right, or slightly ionized I can say. Now students, if I talk about weak electrolyte, the degree of dissociation here is not 100% because they are not breaking into ions completely. Now if I talk about the examples of both of these cases in the strong electrolyte, the examples of strong acid, for example, if I talk about strong acid, it can be HCl, it can be H2SO4. These are the examples for the strong electrolyte. When I take more example in the strong electrolyte only for the strong soluble bases, it basically can be NaOH, KOH, okay. So we can write over here strong soluble bases. It can be your NaOH, KOH. These all basically lies under the category of strong electrolyte, while we can take some example of salts also, for example KCl also in the strong electrolyte case. But when I am talking about the weak electrolyte, in the weak electrolyte the examples are weak acid, weak bases, right? Weak acids such as CH3COOH, okay, and we can have weak bases as well. We can have weak bases also as well as here, okay. So this was all about electrolytes. Now let us learn about Arrhenius theory of electrolytic dissociation. What does Arrhenius told us? This was the very first theory. Arrhenius told about acid and base. What he told? He told that acid is the one in which H positive donates to the solution. H positive ion is donated to the solution. So if I define acid in terms of Arrhenius theory, it is H positive donation to solution. Okay, now if I take one of the example to understand this more clearly, I can say of HNO3. When HNO3 is put into water, that means in the aqueous solution, what happens over here? It dissociates its H positive ion. So H positive ion liberates out, and what do we get? What is the left over here? NO3 negative is left over here. So this is basically what? It is an acid because it is donating H positive to the solution. Now if I talk about the base, it donates OH negative to the solution. If I talk about according to the Arrhenius theory, what is a base? It donates OH negative to the solution, right? Now if I take example of this only, I can take of NaOH. When NaOH is put into the water, aqueous solution, now solution here refers to the water that we are talking about. It splits into which ions? Na positive as well as OH negative. It is dissociated into these ions. Now students here, OH negative is liberated, that means OH negative is donated, hence NaOH is referred to as a base. So this was Arrhenius theory. He explained acid and base in the terms of this condition, right? Now students, if I see more about Arrhenius theory, there were some limitations. This was not applicable to the all cases. What were the limitations? Let us write. What were the limitations? It was a very easy concept that H positive donated is acid, OH negative donated is base, but there were limitations that it was applicable for aqueous solution only. As I've told, they are put into the water, right? So it is applicable for aqueous solution only. This is the very first limitation. Applicable only for aqueous solution. Okay, now students, the second limitation over here, what we got to know that there are some compounds that do not explain the acidic nature as well as the basic nature. Now while explaining the acidic nature, why can't they explain acidic nature? Because they don't have H positive ions. Okay, so we can write they do not explain acidic as well as basic behavior. Why? Because if I talk about acidic behavior, there are some compounds which do not have H positive ions. Now, if they don't have H positive ions, how will they donate, right? Let us take one example. If I take example of CuSO4 over here, does it have H positive ions? No. If I take example of FeSO4, it also do not have H positive ions. So, if they don't have H positive, how will they donate? They won't donate, right? So, this is one of the exception. If I talk about the basic behavior, now there are some compounds which do not have OH negative ions, okay? There are some compounds which don't have OH negative ions. Now students, if they don't have OH negative ions, they won't be able to donate OH negative ions. If I take the example over here, one is Na2CO3, and if I talk about NH3, they don't have OH negative ions. If they don't have OH negative, they won't be able to do so. Hence, they won't be called as a base. But yes, they are base. How can they define be base if they don't have H positive and OH negative? So this was the basic limitation that the Arrhenius theory lacked, right? Now comes students the next theory, if I talk about, that is Bronsted-Lowry concept. Now this was the second concept that again told us about the behavior of acid and base. While explaining through the Bronsted-Lowry concept, he told that acid basically is the one in which H positive ions is donated. It is the same thing as the previous one, that acid basically is the one which donates H positive ion. But here the definition for base gets changes. What is the definition for base? H positive ions acceptor is known as base now. Now base is referred to as acceptor of H positive ions. The donator is acid while the acceptor now here is base. If I take a general example for you, let us take an example of HCl. HCl plus water. Now what happens over here? Cl negative is liberated out and we get H3O positive over here. Now what is happening? See, HCl basically is an acid. We know that this is an acid. And yes, water, water basically has two kind of properties. It is amphoteric in nature. It can act as an acid also, it can act as a base also. So with reacting with HCl, it is acting as a base. Okay. Now, to explain the Bronsted-Lowry concept over here, we can say that it is very well easily seen over here that acid basically is going to donate it H positive. Hence, it is donating its H positive and is converting it to Cl negative. Here, H positive is being donated. Donation is occurring over here. That means this is what? This is an acid because it is donating. While if I talk about water, it is being converted into H3O positive. Forget that this is acid, this is base. Okay, just see the random reaction. Here HCl is being converted into Cl negative. H positive is being donated. Only Cl negative is left over. That means this is an acid, and if I look to the water, water is converted into H3O positive here. Now H positive is being gained, H positive is accepted. That's why it became H3O positive. Now why positive came? Because the charge that H positive carried, right? So this is referred to as base. So if I define over here, acid is the one which donates H positive in the terms of Bronsted-Lowry concept, and base is the one which accepts H positive. Is it clear with this example? Okay, let us see our next case over here. If I talk about the next case, let us take one more example. This was the case in which I took HCl in water. Now I am taking HCl in NH3. Okay. If I talk about HCl plus NH3, what is happening over here? Again, see, HCl is now being converted into Cl negative. What happens over here? We get NH4 positive. Now, kindly tell me which is acid, which is base. It is quite easy for you people now. How? See, HCl is now being converted into Cl negative. Now, it is being donated its H positive ion. So, here, donation of H positive ion is occurring. That means it is an acid. Now, if I talk about NH3, it is now being converted into NH4 positive. Now, there is an acceptance of H positive ion. So, basically, it is what? It is a base. So, I hope so this example is very well clear to you. Now, the very important thing that you need to remember is strong acid will give weak conjugate base. Now, listen to this very carefully. Strong acid will produce or will give weak conjugate base. Okay, strong base will give weak conjugate acid. Okay, now if I say these are for the strong case, if I say for the weak acid will give strong conjugate base, while weak base will give strong conjugate acid. So this is really very important for your examination's sake. Kindly put a star over here. This can be asked whenever you are taking a strong acid. That means whenever you are donating any H positive ions, the base that is produced is going to be weak conjugate base. And whenever you are taking a strong base, okay, that means that will, what it will do, it will basically accept H positive ions. So the acid that is going to be produced over there, that is going to be weak conjugate acid. Now if I talk about weak acid over here, whenever you are taking a weak acid, it is going to donate its H positive. When it is going to donate its H positive, what is going to be obtained over here? Strong conjugate base will be obtained, just the opposite of it. And whenever you are taking the weak base, what is going to be obtained? Strong conjugate acid is going to be obtained. Is it clear? Great students. Now let us see the very next thing, that is the amphoteric substance. Now as I've told you, water acts as an amphoteric substance. So what do you mean by amphoteric substance? Let us write this also. What do you mean by amphoteric substance? A substance basically which acts as acid and sometimes as base also is referred to as an amphoteric substance. So we can write substance which act as acid and sometimes as base also is referred to as amphoteric substance. Amphoteric substance. Now if I talk about water, water acts as an acid also, as an base also. Let us take two examples for this. If I talk about CH3COOH, I am taking water with this. The next example that I am taking is, the next example over here is NH3 plus water. Now students, if I am taking both of these cases, in the very first case I have taken CH3COH, which is an acid. I know that this is an acid. So when CH3COH is an acid, students, the water will act as a base. Okay, so it will act as a base. Now we know that acid is the one which is going to donate its H positive ion. So it will be converted into what? CH3COO negative. While students, base is the one which is going to accept H positive. So here this base is going to accept H positive and will be converted into H3O positive. Is it clear? Now here you can see the next case when we have NH3 plus H2O. Again here what happens? NH3 we know is a base. Now when this is the base, students, the water over here will act as an acid. So you can see acid, you know, water is somewhere acid, somewhere base. So it has both the properties, hence it is amphoteric in nature. Now come back to this part. I am saying that base is the one which is going to accept H positive, while acid is the one which is going to what? Which is going to donate. Now if H2 is going to donate its H positive, it will be converted into what? OH negative. While now H positive is left over, which will be accepted by the base. Now this will accept and it will be converted into NH4 positive. Is it clear? So you know, by this practice in practice you are able to do so the reactions also. Now let us move towards our next part. Now comes the limitation part. See, we saw the Arrhenius theory. Now we are looking to the Bronsted-Lowry concept. What is the limitation? There were some things that were unable to be explained by the Bronsted-Lowry concept also. So we are going to do the limitation section over here. Limitation section. Now if I talk about the limitations for this, see, the very first limitation that came in our mind is they cannot explain the acidic behavior. For example, in CuSO4, in AlCl3, because they don't have H positive. So if they don't have H positive, they won't be able to, you know, donate it. So I would say they were not able to explain the acidic behavior. The acidic behavior. Now as they weren't able to explain the acidic behavior, we can take the examples also. For example, in CuSO4 I can take just the same case. In the previous also this was the problem, in this also this is the problem, and in AlCl3 because they don't have H positive. So when they don't have H positive, neither they can, you know, donate nor they can accept, right? Now if I talk about, this was for the acidic behavior. If I talk about the basic behavior, the one which can't accept proton, they were not able to explain basic behavior. Why? Question rises why? Because they were not able to accept proton that is H positive, right? Example is calcium oxide, MgO, magnesium oxide. Okay, so this were the limitations for your Bronsted-Lowry concept. Now comes Lewis acid. If I talk about Lewis theory, Lewis explained Lewis acid based theory, we can say in other terms. Lewis acid is the one in which electrons, you know, the acid is the one which accept electrons. In the terms of electrons we say this, it is the one which accepts electron. Okay, now let us see the examples over here. For the Lewis acids, they are cationic. How? All simple cations act as Lewis acid. For example, H positive, Ag positive, Fe+2. See, electron basically is a negative charge species, and the one which is positively charged species will only require electron to become a neutral species, right? So the one which is already negative will not gain electron because negative and negative repel each other. So positive will only attract electron towards it. That means all the cations will come under the category of Lewis acid, right? So Lewis acid, we can say all simple cations act as Lewis acid. Example, H positive, Ag positive, Fe+2. Now electron deficient molecules who require electron, you know, I am going to take a case of BF3 also in the after explaining what is Lewis acid, Lewis base. First of all, see, electron deficient molecules in which octet of central atom is not complete, who require electron. Okay, so example is AlCl3, BF3, BCl3, BeCl2, etc. These also comes under the category of Lewis acid. The last category is molecules whose central atom can show expansion of octet due to availability of empty d orbital. Now there are some molecules which have the capability to form more bonds, right, due to the availability of empty d orbitals. Now the d orbitals can participate in the bond formation. So here Examples are SiX4, GeX4, SnX4, PX3, PF3, SF3, TeCl3, SEF. These all are Lewis acid. Is it clear? Okay, if I talk about Lewis base, what do you mean by Lewis base? These are the one which donates electron. Now, when we were talking about Arrhenius theory or the Bronsted-Lowry concept, we talked all about H positive, OH negative, all of these concepts. Now we are talking about acid and base in the terms of electron, right? So Lewis base is the one which donates electron. Now it is going to donate electron. Now who is going to donate electron? Who already have electron, they will donate. That means who already have a negative charge, they will donate its electron, right? So here, first of all, the neutral species, they are saying having at least one or more lone pair of electron, which already have one or more than one lone pair of electron, they will donate electron because they have efficient amount of electrons, right? Available at the central atom. For example, PH3, NH3, ROH, RNH2. Now here phosphorus has a lone pair of electron, here nitrogen, here oxygen, here nitrogen. So all of these lie under the category of Lewis base because they can donate electron very easily. Now next comes the negatively charged species. Why negatively charged species, students? Because negatively charged species is already negative. They already have electrons. So they have the tendency to donate it, right? So all the negatively charged species or ions, for example, Cl negative, Cn negative, OH negative, X negative, NH2 negative, SH negative, when they will donate, they will become neutral. So they do want to donate it to become stable, right? So they all come under the category of Lewis base. The third category is molecules having a multiple bond between atoms of dissimilar electronegativities. Now what do you mean by electronegativity? Electronegativity is the tendency to attract shared pair of electron towards itself, right? So here the molecule who have a multiple bond with the different electronegativity, they also come under the category of Lewis base. Clear, students? Now let us see the case in which I will explain you both Lewis acid and Lewis base together. So let us take the case. I have just told you all the examples. We are taking BF3 and we are taking, NH3. BF3 was our Lewis acid, right? Because it had a deficiency of electron. It want to accept electrons. While if I talk about NH3, we just have seen that NH3 has nitrogen, has a lone pair of electrons. Now what will happen over here? This nitrogen will donate its electrons to the boron. When it will donate, now this will donate its electrons, so this is referred to as a base. When this will accept electron, this is referred to as an acid. So here a coordinate bond will be formed in both of these and it will look like this. BF3 coordinate bond to nitrogen, hydrogen, hydrogen, hydrogen. So this is what we obtained from here. So this is our Lewis acid, this is our Lewis base. Is it clear to you? Great, students. Now students, if I talk about the next topic, let us understand about dissociation constant for weak acid and weak base. Dissociation constant for weak acid and weak base. If I talk about dissociation constant, basically dissociation constant we will write for acid, that is going to be Ka, and for base that is going to be Kb. If I talk about general case acid, if we take Ha as an acid, now it will split into what? H positive and A negative ion. We know this. Right, now students, while writing the dissociation constant, what do we write? We write the concentration of product divided by concentration of reactant. We are talking about an acid, this is an acid. So dissociation constant for an acid, that is Ka. Ka is dissociation constant for acid. Now it is equivalent to what? The concentration of the product divided by the concentration of reactant. So the product over here is H positive and A negative, while the reactant over here is Ha, right? Similarly, we can write a reaction for the base. Now, let us take an example for the base. For example, if I say BOH, now it splits into what? B positive and OH negative, right? Now, for this base, we are going to write dissociation constant Now dissociation constant for base is going to be Kb. See, A for acid, B for base, right? Now for here, we are going to write the concentration of the product divided by the reactant. The product here is B positive and OH negative, while the reactant over here is BOH. Is it clear? So by this way, we can write the dissociation constant for both of these cases, for the acid as well as for the base, students. Now students, moving to the next part is ionic product of water. You know, this is a really very asked question. Ionic product of water. How to calculate it? Ionic product of water. See, for dissociation constant for water we write Kw, for acid we write Ka, for base we write Kb. Now for water we write Kw. Now what is the reaction for water? Again, if we write H2O, it dissociates into H positive as well as into OH negative, right? It dissociates into the signs. Now if I am writing for this case, all I would say is that it is a direct situation. How you can do? Kw is equals to the concentration of product H positive OH negative divided by the concentration of reactant, that is H2O. Now you know the water is present in a constant amount. So this can be taken this side. If this is in constant amount, it will be Kw into concentration of water is equivalent to concentration of H positive into concentration of OH negative. Hence this is constant, so we can neglect it. So directly what do we obtain over here? We obtain Kw, that is dissociation constant for water, is equivalent to H positive into OH negative. Here you can write dissociation constant for water, for H2O. Right? Now this formula we have derived over here. Now the thing that arises is, you know, when you have H positive and OH negative ion and you say that water is constant, the concentrations for both of these according to the pH level, maintaining the pH level, the concentration for H positive is 10 raised to the power minus 7, while the concentration for OH negative is 10 raised to the power minus 7 at the room temperature at 25 degrees Celsius. So if I talk at 25 degrees Celsius, what I obtain from here, that the concentration of H positive at 25 degrees Celsius is 10 raised to the power minus 7, and the concentration for OH negative is also 10 raised to the power minus 7. So if I put the situation over here, what I am getting Kw is equals to concentration of H positive into the concentration of OH negative. That means 10 raised to the power minus 7 into 10 raised to the power minus 7. So when they are, they have been given into the multiplication, you have to add the powers. The base are same and they are in multiplication, the powers are added. When the base are same and they are in divide, the powers are subtracted. So here 10 raised to the power minus 7 plus minus 7, so it comes out to be 10 raised to the power minus 7, which is equivalent to 10 raised to the power minus 14. So we can say that here dissociation constant for water at 25 degrees Celsius, this is at 25 degrees Celsius, comes out to be 10 raised to the power minus 14. Now students, what is the effect of temperature on Kw? You know, whenever you are going to increase the temperature, the Kw value is also going to increase. So this is also important thing that you need to remember in this section. Clear? Again I am repeating, this is at 25 degrees Celsius. At other temperature you can calculate also if the concentrations are provided to you according to your this formula. Kw is equals to H positive into OH negative concentration. Okay students, now let us see the pH scale. If I talk about what do you mean by pH scale, basically pH of a solution may be defined as negative logarithm of hydronium ion concentration. Okay, now here hydronium ion, or we can say in other words, we can directly write pH is equals to minus log of H positive. We can write this also, it is the same thing. Do not get confused in this. Okay, now here, in other terms, if they ask you about the concentration for this, that will be 10 raised to the power minus pH. There is no need to do so. There is only one formula, either you do or you do this. These both are important, right? Similarly, we can define POH as POH is equals to, now this is for POH. For POH, this is for pH, now this is for POH. It is equals to minus log of OH negative, okay, in the terms of OH negative. Now the pH range at 25 degrees Celsius is taken from 0 to 14. I hope so, you know this very well. If the pH level is 7, then it is said to be neutral. It is said to be neutral. If the pH level basically is more than 7, it is basic in nature. When it is less than 7, it is acidic in nature. This is the very basic thing that you need to keep in your mind. Other than this, students, first of all, we are going to start with the common ion effect. You know, what do you mean by a common ion effect? Now, you know what is pH, okay? If I talk about common ion effect, its name itself says there is something common. An ion is common in the two reactions, right? Now, let us take one case of CH3COH. It is dissociated into what? It is dissociated into CH3COO negative plus H positive. This we know very well. Now we are going to take HCl case over here. When I take about HCl, it is a strong case, right? Strong electrolyte, it will be dissociated into H positive and Cl negative. Now what we are obtaining from here? We are looking that we obtain that here H positive are common in both of these reactions. Now when H positive are both common in both of these reactions, and when CH3COH was present initially but we added HCl in it, so what happened? What happened? In the product side, H positive concentration increased because initially this reaction was occurring, but when we added HCl in it, this reaction also started, and when this started, H positive was produced in high amount due to the production of H positive in high amount. You know, the product side increased. The product side reaction, product increased, or I would say product concentration increased in other terms. Now when the product concentration increased, what was according to the Le-Chatelier's principle that we studied in the previous lecture? According to Le-Chatelier principle, whenever there is a change occurring in any of the reaction, it will undo their effect. So here, if this side is being increased, it will convert it back into the reactant so that this is undo. This will undo the effect of that, right? So if this side is increasing, this will undo this effect. If this side is increasing, the reaction will proceed in the forward direction. When the product side is increased, it will proceed in the backward direction. Hence, we can say that the backward reaction occurs, and the chances of backward reaction also increases. So this is basically the common ion effect that you need to identify in the particular two reactions, which of the following concentration is being increased. Clear? If the reactant is being increased, it will be converted to the forward reaction. If the product is increased, it will convert it back into the reactant to follow the Le-Chatelier principle. Clear? If you forget the Le-Chatelier principle, you can see the previous lecture also, students, for chemical equilibrium. Now we can take two cases over here to understand in depth. That means two solutions we are going to see. Now what are the two solutions or two cases, I would say? The very first case that I talk about is of weak acid plus salt. We are going to take weak acid plus salt and we are going to obtain an acidic buffer from this. We will obtain an acidic buffer. Clear? Now the next state or next solution case that we are going to take is weak base plus salt. When we are going to take weak base plus salt, students, we are going to obtain basic buffer. We are going to obtain basic buffer. So these two cases now we are going to see in detail. Let us see the very first case over here. Now, okay, if I talk about, students, the very first case, that is acidic buffer. If I talk about acidic buffer, let us take our weak acid, that is, let us see acidic buffer. It is CH3COOH. This is the weak acid. Now what we are going to see, it is split into its ions. Now what are the ions? It is CH3COO negative plus H positive. Now we told that weak acid plus its salt. Let us take a salt. What will be the salt for this ion? See, CH3COO negative when combined with H positive becomes a salt. Now we have taken weak acid, we have taken its salt. It will be split into what? It will be split into CH3COO negative and Na positive as well. Now what is the common ion over here? The common ion over here is CH3CO negative, which is present in both of the reactions. Now again, the concentration in the product side is increased, but of whom? of CH3CO negative, but we usually talk about pH, and while talking about pH we talk about H positive ions. So what is the concentration of H positive ions over here? The concentration of H positive ion decreases. Why? Because the CH3CO negative ion concentration increases. So we can say H positive ion concentration is decreased. Now we know that students, pH is basically minus log H positive concentration. So basically if H positive is being decreased and pH has a negative sign over here, hence we can say that pH for this will increase. So if H positive ion concentration is being decreased, the pH will increase. This is basically an acidic buffer. Now similarly we are obtaining the next segment over here, that is the basic buffer. Now if I talk about the basic buffer, that is going to be NH4OH. Now if I talk about NH4OH, it will again split into its sign, that is NH4 positive and OH negative. When it will split into NH4 positive plus OH negative, students, this is the very first case. Now we are going to take the salt. We will take the salt with this case only, NH4 plus, then when it will be reacting with another anion, it will be Cl negative, it will combine to form NH4Cl. It will split into again NH4 positive plus Cl negative. Now what is the common ion over here? We have again taken, to make a basic buffer, we have taken weak base and its salt, right? So here we have NH4 positive, we have NH4 positive as a common ion. So I can say that over here NH4 positive ion concentration is increasing, but we have OH negative. So OH negative concentration is decreasing because this is in more amount. So we can say over here OH negative is being decreases. Okay. Now if OH negative is being increases, that means H positive will increase. It is but obvious, it will increase. Now if H positive increase, what will be the effect on pH? We know that pH is equals to minus log of H positive. Now if H positive is being increased, there is a negative sign, hence we can say pH decreases. Now for basic buffer and acidic buffer, it is a total almost a different scenario. Okay, so you have to see this in very detail. Now students, this was the preparation of acidic and basic buffer. Now there is a relationship between both of these, is that when you talk about the ionic product of water, that it will be equivalent to Ka into Kb. Now what was Ka? It was dissociation constant of acid, into Kb, that was dissociation constant for our that base, right? Now students, come the factors affecting the acidic strength. What were the factors that affect the acidic strength, right? So if I talk about the factors, the very first factor is weaker the HA bond. The weaker the HA bond, what will happen? More easily it will get dissociated. More the weak bond, more will be the dissociation. It will be easily broken up, right? Easily it gets dissociated to give H positive ion, and hence the stronger is the acid. So this is the very first important point, that the more the weaker bond, more the dissociation. Easy the dissociation, stronger is the acid, because acid is the one which is donating H positive. So easily the donation, easily it is the strongest acid. Now next is greater the polarity of the HA bond. Polarity refers to the difference of the electronegativity. It arises due to the difference in the electronegativity. Now again, what is electronegativity? Electronegativity is the tendency to attract a shared pair of electrons towards itself. If I talk about this HA case over here, they are saying if they make poles, that is the positive and the negative ions over here, larger the electronegativity difference, okay, between the atoms, between H and A, more easily the bond breaks. More the electronegativity difference, more easily will the bond break, and hence greater is the acidic strength. So this is very, very important for you all. You have to write this. Okay. Next is example. Okay, they have taken for the element of group number 17. They have taken HF, HCl, HBr, HI. Now acidic strength they have been given you. This is for the acidic strength. Larger the difference in the electronegativity, they say more easily the bond breaks and greater the acidic strength. Now similarly for the elements of 16, they have given you the acidic strength order. You can write it. Okay students. Now comes the next factor for the elements along the same period that were for the particular groups. Now they have been given for your same period. How you will calculate the polarity of the HA bond decides the acidic strength over here again. Okay. With the increase in electronegativity of A, the polarity of the bond increases. You know, the electronegativity increases, the polarity increases because the charges are arised over here. Positive and negative charge dissociation is seen, right? And hence the acidic strength also increases. So they have given you an example of CH4, NH3, H2O and HF. They have told you acidic strength increases, electronegativity increases and the polarity increases. So basically it depends upon the polarity. More the polarity, more will be the electronegativity difference, more will be the acidic strength. Now students, comes our next segment, that is important one, that is buffer solution. Okay. Now students, if I talk about buffer solution, let me have a glass of water. Till then please revise the factors affecting. Okay students, now if I talk about the buffer solution, let us see for the buffer solution, when acid or base is added to water, what happens? pH changes. Now buffer solution is used to resist the change of the pH. They don't want the pH to change, so we use a buffer solution. What happens? I am repeating again. When acid or base is added, when they are added together, there is a change in pH. They are added to water, there is a change in pH. Okay, now there will be a change in pH. To resist this change, buffer solution is prepared. Now buffer solution resist the change in pH when acid and base are added to water. They are added to water. Okay, now how to obtain buffer solution? This is really important. Let us see how we will get to know about the buffer solution. First of all, we will prepare acidic buffer and the basic buffer. We have already seen. I'll repeat again. Acidic buffer is the one in which we have taken weak acid and its salt, and we prepared acidic buffer in the previous case. Now, how will basic buffer be obtained? When we take weak base and its salt. The basic buffer will form. We will use the common effect. Now the important formula, students. This is really very important. Kindly put a star mark over here. If I talk about acidic buffer. See, for acidic buffer, there is a formula to calculate the pH. Now, for acidic buffer, we know that K is the dissociation constant. To calculate this, the pH for acidic buffer, pH basically is equals to pKa. Now, pKa plus log salt divided by acid. The concentration of salt divided by the concentration of acid. This is the formula that you're going to apply in the numerical sections again and again. If I talk about the basic buffer, for the basic buffer, now we are going to obtain pH. No, for basic we are going to write POH, right? For basic buffer, if we are writing POH, it will be equal to what? It will be equal to pKb. Why pKb? Because Kb is the dissociation constant for the base, right? So we will write over here pKb. Now what happens? Plus log concentration of salt divided by concentration of base. Now here base will come. Clear? These two formulas are really very important, so kindly put a star on both of these formulas. Okay, now students, this was the formula of acidic buffer and the basic buffer. Now comes different situations that we need to keep in our mind. What are the different situations? See, if I take case, we are going to see the 4 cases now. We are going to see 4 cases. The very first case that I talk about is strong acid plus strong base. This is the very first case that we will talk about. See, if we are taking the case for strong acid and strong base, the pH level for the strong acid and strong base, when they are added together, the pH level is 7. the pH level over here is 7. So there is no need to calculate pH for this because it is almost 7. It is totally 7. Clear? Now if I take the next case, when I say there is a strong acid plus weak base. This is my second case. When I am taking strong acid plus weak base, how to calculate pH? Now over here, the pH basically is less than 7. This is really important. pH is, if it is less than 7, then in the formula, you will observe a very different thing. Okay, see, when we will write formula, we will write 7 minus. We are obtaining pH for this. For strong acid weak base, we are saying 7 minus. Why 7 minus? Because pH is less than 7. If pH was more than 7, then we would have added. But it is less than 7, 7 minus will come. Now what will happen? Half into, now we will write log. Log of what? We are talking about what? We are taking strong acid and weak base. So we will write here pKb plus log C. This is your formula for strong acid plus weak base. Now comes the next two case. Let us see the next two case. Now in the third case, that is quite similar to the second one. It is weak acid plus strong base. It is weak acid plus strong base. If I talk about weak acid plus strong base, here the pH level basically, here the pH level is more than 7. When it is more than 7, I have just now told you, when it is less than 7, you have to subtract from the 7. When it is more than 7, then you have to add in 7. So the pH that came over here comes out to be 7 plus. Now we are going to add over here. Now what we are going to add over here? Log pKa plus log C. Okay, this is the formula for your weak acid plus strong base. Now students, comes our last case when we are talking about weak acid plus weak base. See, if I talk about weak acid plus weak base, it is very simple. See, here it is approximately equal to 7 plus half. Now bracket starts here, pKa minus pKb. pKa minus pKb. Kindly put a star on all of these formula, on 4 of these formula, because these are quite important for your examination point of view. Now students, comes our last segment, that is solubility and the solubility product. What do you mean by solubility and the solubility product? First of all, here kindly put an arrow, it is missing, sorry for this. Okay, the number of moles of a solute in 1 liter of a saturated solution, and its unit is given mole per liter, is defined as solubility. Now what do you mean by solubility? It is number of moles of solute in 1 liter of a saturated solution. Clear? Now let us calculate solubility of salt AXBY. Now we have been given AXBY, our salt. It will be split into its ions, right? Now here we know that. Why they have written in such a way, I will explain you. See, while if I talk about how is water formed, this is not concerned with this case. I am telling you about the charges. See, if I talk about water, I know that hydrogen has a positive charge while oxygen has -2 charge. The charge on oxygen will move under the charge on hydrogen will move under the oxygen, and the charge of oxygen will move under the hydrogen. That means hydrogen will have at the base 2 and oxygen will have at the base 1. This is how it is formed. So if I come to this general case, see, we have AXBY. That means Y is the charge on A. Okay, Y is the charge on A and X will be the charge on B. Now why it is written plus Y and minus X? Because initially we write cation and afterwards we write anion. So first of all, the positive species will be written and then the negative species will be written. It is quite clear to you. Now according to this we have divided. Now ma'am, you will say why X and Y? This X and Y is done in order to balance the equation. Clear? So this is the general case when we have taken a salt. It is split into its ions in the aqueous form. Now what is happening over here? for a saturated solution, that means at equilibrium, what state do we get? What is the value for the equilibrium constant? If I talk about K equilibrium over here, what I obtained is the concentration of product. Now here, this is my first product, this is my second product, divided by the concentration of reactant. Now what I will do, as I have done in the water case, this will move on this side. I have brought Ax By on this side. What I am obtaining over here, this is the concentration of the product side. Now this basically, students, this basically is known as KSP. Now what do you mean by KSP? KSP is referred to as the solubility product. It is referred to as the solubility product. This all is equivalent to KSP, which is equivalent to this. That means to the product side concentration. This is KSB, solubility product, just as we did in the water case, ionic product, just as we did in the acid case, in the basic case. Now let us take two examples for this to understand more clearly. The very first example is AgCl. See, if I talk about AgCl, students, basically it splits into its ions, that is Ag positive and Cl negative. It is quite simple. It will split into Ag positive and Cl negative. Now when we are talking about the concentration for these aqueous ions, we say that, let us say the concentration for Ag positive comes out to be small s, and the concentration for Cl negative also comes out to be small s. Now I have already told you what is the value for Ksp. The Ksp comes to be the product of the concentrations product on the product side. So here we will say Ag positive concentration into Cl negative concentration, that means S into S comes out to be Ksp. Why we have not taken the reactant? Just I have shown you in the previous case. See, here this was the state, we took the reactant on this side and we told that this basically is Ksp, which is equivalent to the concentration of the product, the multiplication of the concentration of the product. So that's why we are directly writing this formula over here, and we are directly writing this, that Ksp is basically is equivalent to this. Now Ksp is equal to what? Ksp is equal to K equilibrium into the concentration of the reactant. Is it clear? Now to obtain what? We have obtained solubility product over here as S square. Now if this is your first formula, if they ask you to calculate the concentration, how we will calculate the concentration? Concentration, that means S comes out to be square, will make it under root, that is under root of Ksp. These are the two formulas obtained from this case. Now let us take one more case. If I take one more case, the last case is CaF2. If I talk about CaF2, it is split into Ca plus 2 plus F negative. Right now, students, it is quite different. Why it is quite different and interesting? See, here there is one calcium, here there is one calcium, but here there is two fluorine, here there is only one, so it will be balanced. See in the previous case. Why I have written this X and Y? So that we can balance it out. This is really important. Students skip this step, and which will lead to the wrong answer. So do remember this, balancing is important. Here you can see one Ag was there, one Ag was there, one Cl was there, one Cl was there. But here what happens? One Ca, one Ca, two F, and here one F was there, so we multiplied with 2. Now we will assume again here, let us say the concentration for this is S, and now the concentration for this is S, is correct? No. We have 2F, so the concentration comes out to be 2S. Now what will be the value of the solubility product over here? We will say that KSP, solubility product, is equivalent to the concentration of Ca plus 2 as well as the concentration of F negative now, as well as the concentration for F negative. So what will happen over here? It is S into, it is 2S, but this is wrong. Again this is wrong. Why this is wrong? Come back to this situation. See, if I come back to the situation, what I observe over here, what I observe that there is a Y number over here that is present. That Y will come at the power of this. If this is present over here, if X is present in front of here, it will come in the power of this, and if Y is present in front, it will come in the power of this. So we can write over here that basically what is happening, if this has 1 over here, the power is 1. If it has 2 over here, the power is 2. If here there is 1, the power here is 1. If here there is 1, the power here is 1. Okay, but here there is 2, so the power comes out to be 2. That means it is square of this. Now to solve it further, we can say that S into, now 2S square refers to as 4s square. Now s into 4s square, first let us take the number out. 4 into s square, it comes out to 4 into s cube, right? So the KSP value comes out to be 4s cube. This is your first formula for this situation. Now if I ask you the concentration of the S or the solubility of of Ca plus 2, then you will find the value for S. S comes out to be cube root. Cube root is written in such a way. Cube root of basically KSP divided by 4. Is it clear to you? It will be the cube root of KSP divided by 4. So by this way, students, you can find out the solubility product. So yes, my dear students, this ends our lecture over here, the ionic equilibrium over here, and this ends our physical chemistry of class 11th also. I would recommend for this question segment, you can open your DPP that is being provided to you. You have to solve all of the questions. The formulas which I have provided to you will be able to complete all of the questions in that area, right? Now students, your suggestion that I would give you is that practice more and more questions. By practicing more and more questions, you will be able to attempt your examination very well. And the second thing, when you are unable to practice any of the topic, kindly go back to the video. You have been provided with all of the videos of the physical chemistry of the class 11th. So you can go back to that lecture, to that particular topic, re-revise it, re-revise your notes and apply that concept into the numerical section. Okay. So thank you so much. I wish you all the best for your examination. So keep smiling, keep learning. Thank you so much. Have a good day.